events for today. We have to finish the bilateral function and how it's related to HDR, another application of bilateral functions. We want to talk a bit about ambient shadows. We want to start animation, but most of all, we want to hear.
This is my advisor.
Hi.
Hey.
Very excited to meet you.
Same here.
I'm good to start. Yeah.
In
Okay.
end of the semester, we know people have projects in OS and compilation. They might come, they might not.
OS.
Yeah.
I see. All right. Well, I'm going to just talk about some of what I do for my research over in OpSci, kind of pictured here. The reason I'm taking this class in CS is that my research actually has to do with ray tracing for physics-based rendering, specifically looking at polarization as an aspect of rendering. So ray tracing from an optical perspective is a really good way to simulate how light moves through a system, which is the fundamental question that optics is really trying to answer. How does light behave? It can be used to predict image formation, aberration, things like that, which is shown kind of here as we propagate through a system. And we already know that we can have different types of physical interactions like reflection, absorption, also like diffusion and scattering. These are the different types of physical interactions we're seeing when we're painting a surface, say, in computer graphics. And optically, when we talk about array and ray tracing, we're really talking about the direction of energy flow for an electromagnetic wave. And when we talk about the polarization of light, we're talking about the orientation of an oscillating electromagnetic wave. So every ray is really this oscillating field, and that field can have different orientations. So it also can be different amounts of polarized. So here we can see this field is oriented at 45 degrees. And as we decrease our degree of polarization, we're basically increasing the amount of randomness in the likelihood that we get that preferential oscillation in 45 degrees. So why would polarization matter in ray tracing? That's kind of like, why am I taking this class? Well, many common objects affect the polarization of light. And just to give one example that I like is a pair of sunglasses sitting on a table at the beach. So this image is actually generated using AI, and can anyone like spot the AI obvious
Yes.
AI effects? Like what? Very smooth. I notice immediately as like an optics person, like the shadows are wrong. There's a gap in the shadow here, but it's like not right. But the other thing that we would really be trying to answer when we talk about polarization is, what's this image in the sunglasses actually look like? Polarized sunglasses are a great example of how we induce polarization. And if you have a pair of polarized sunglasses, you can actually look up at the sky and see like a dark band in the sky, and that has to do with how the skylight is partially polarized. It doesn't go all the way to black because it's not completely polarized, but part of the sky is polarized, and that's a really great example. We can also use polarization cameras to visualize polarization, and here are the effects of two different types of lighting. So we can see in sunny conditions that this angle of polarization with the dome on the other side of campus, just across from the optics building, we get this radial pattern. But when we have cloudy conditions, that's more diffuse lighting from the atmosphere, and we get a totally different tangential polarization pattern. So polarization doesn't just depend on an object's geometry, it's going to depend on the lighting as well. Polarization in common environments, here are some examples. So first of all, here is two pictures of a desk with the light on and off, and we can see that the polarization signature changes significantly when the light is on versus off. Specifically looking at the top of the laptop, this is really smooth, has a really smooth profile and is close to horizontally polarized red, whereas this is like blue and green and really noisy, and it's up in this vertical part. Water is another great example.
The assumption is that the other source is light from the sunlight.
Just ambient room light, right? With the lamp off, this is like ambient.
Like an incandescent, or is it a
Yeah.
fluorescent maybe?
Yeah, like a fluorescent light in the ceiling. And then we just had our homework on reflections from a pool. This is a really great example and connects directly to photography, where we can use polarizers on our cameras to reduce glare from water, because certain polarizations are more likely to transmit through the water, the vertical polarization, whereas the horizontal is more likely to be reflected. And so this is kind of just a motivation for this project, why in ray tracing we would need to consider the polarization to get accurate scene renderings. So mathematically, then how do we translate that into an algorithm? Well, the simplest way to describe polarization is using Jones calculus. So one of the rules, if you ever took like intro physics with E&M, maybe you learned that the electric field is always perpendicular to the magnetic field, which is always perpendicular to the direction that the light's traveling, right? So if we say that the light is traveling along the z direction, then our oscillations are only going to be in the xy plane. And for a Jones vector, all we do is we take the x and y components of the electric field vector and write that in a 2 vector. Now, each component of this 2 vector is going to be complex because we have the amplitude of that, and then we also have the phase relative in the x and y. So we have to use complex numbers, and here are some examples. So we can have 45 degree. So this is half of it is in x, half of it's in y. If we have circular polarization, we actually have a phase difference between the x and y, which causes this vector to kind of rotate and trace a circle over time. But we're not actually doing any time evolution, we just represent that using complex numbers. And then we can also have like elliptical. And to model how a system transforms these Jones vectors, we use a Jones matrix, and there are different types of effects that we can see on polarization. Basically, we can see relative phase changes, we can see different amounts of polarization, right? We can see polarization that's horizontal go to vertical or vice versa. And all of that's represented with a 2x2 Jones matrix. The one problem with these is that they can only represent fully polarized states. And as we showed kind of with some of those earlier images right here, we only have partially polarized reflections from the water. So we need a way to represent partial polarizations. And that uses a different formalism called Stokes parameters. A Stokes vector has kind of your overall intensity or brightness for the ray, and then we talk about the Q, U, and V components, which come from the amount of horizontal 45-degree linear and right-hand circular. And we represent that using the Poincare sphere, which is kind of a cool trick that basically makes this, I think, a lot easier to visualize if you're more of a visual person. So think about this as a 3D unit sphere. Anything that's on the surface of this sphere is going to be a fully polarized state, right? The square root of this thing is the same as I, so that's 100% polarization. That's on the sphere. And then inside the sphere is our partially polarized states. The equator of this is all of our linear states, and then the upper hemisphere is going to be our right-hand elliptical states, and these are our left-handed elliptical states, which is basically just which way is that circle rotating over time. Is it rotating to the left or to the right?
I'm not sure. I thought what are partially polarized is the combination of polarized plus random direction plus white noise.
Yeah, so you could basically think of it as this percent polarization is the preference towards that. So the partially polarized state, kind of again going back, ooh, that's the wrong way. Where was it? The partially.
It was like slide 3, it was pretty early, where you had the scrambles.
Yeah, that's what I was looking for. Right here.
Yep.
So this is like a 40% polarized.
Yep.
You can see it's some randomness. 0 would be all the way around. And the way that we would manipulate a Stokes vector, similar to a Jones vector, is with something called a Mueller matrix. And the Mueller matrix is going to be 4 by 4 since we have a 4 vector. So that's an important thing to note. If we are trying to choose one of these formalisms for ray tracing, in Jones calculus, we have a 4-element complex matrix, so we need 8 total numbers to represent that. With the Mueller matrix, we're doubling that up to 16 real elements. So immediate comparison, it seems like Jones kind of offers a little bit more simplicity. Another advantage of Jones calculus is because they're sharing an X, Y, Z basis with our global system, we can perform quaternion rotations on Jones vectors. However, we can't do that with Stokes vectors because they're in that Poincare space rather than being in our XY coordinate system. However, the most important difference is that here, Jones calculus is only fully polarized. Mueller calculus, we have partially polarized states. And if we look at a common indoor scene, there's a lot of partial polarization. Here's a image which shows the degree of linear polarization. And I want to highlight this is on a log scale. So really most of what we're seeing in this back wall is like single-digit polarization for most of this. So we need to be able to represent partially polarized states in indoor environments. But we would love to be able to take advantage of kind of the simplicity of Jones calculus. So the current standard for rendering polarization is the Mitsuba physics-based renderer. Right now, Mitsuba 3 is their latest release. This does spectral path tracing, and it has lots of plugins for different types of sensors and camera optics that can simulate all of the different effects that we would see of a real imaging system if we want to have like a really accurate rendering. And this can scale across both CPUs and GPUs in different operating systems. Mitsuba does come with current polarization support using those full 4x4 Mueller matrices, tracking the Stokes vectors in this path tracing, and the kind of drawback of using Mitsuba with global illumination for this polarization rendering is these images take on the orders of hours to generate. A simple scene, something like this would take 3 or 4 hours to render. And we're really trying to see, can we do this in real time? Like, especially with AR and VR becoming more common, we want to try and speed things up. So, our unique approach to acceleration, we are taking the key idea that polarization comes from these surface interactions that generates some, but not a huge amount of polarization. But that's still going to follow the structure of our scene like we saw earlier in that tangential versus radial pattern on the dome, depending on the lighting conditions. So in order to model that, we want to take our 16-element Mueller matrix. This matrix has 16 degrees or 15 degrees of freedom if we set this top value to 1 plus an overall intensity. And we are going to basically make an assumption that the depolarization degrees of freedom are not independent. And by doing that, we do lots of math that I'm not going to go over for the scope of this, but we can basically take this Mueller matrix and approximate it as 4 Mueller-Jones matrices weighted by these eigenvalue weights that we get from eigenanalysis. And so what we'll do is we'll assume that these smaller weights of these 4 component Mueller-Jones matrices, sorry, I should say what a Mueller-Jones matrix is. So we know that Mueller matrices can introduce depolarization. Jones matrices can't. So every Jones matrix has an associated Mueller matrix, but it's not necessarily the other way around, sort of like how a rectangle isn't always a square. And so we're getting 4 component Mueller matrices, which are also Jones matrices, and that gives us, the total of 16. By assuming equal weights, we're going to then model 1 as an ideal depolarizer and simplify this so we only have 1 Mueller matrix, which is also a Mueller-Jones matrix and lets us use that simpler Jones framework by making this assumption. And so we get this new equation. And our hypothesis...
So is this a matrix you compute for every patch of the surface for every source of light?
So there's different ways to do it. You can use like an analytical BRDF, or we can do measurements in the lab. And I'll get to kind of how we're doing it right now and where we want to go with it at the on the next slide.
In the perfect world, once I know my sources of light at the room, I want to attach to every edge or obstacle such a matrix that will, similar to the BRDF, will tell me how it behaves with respect to every form of polarization of light falling on it?
Basically, so we're going to take the BRDF and make it matrix valued, is what we're doing. So instead of having a scalar BRDF, it's just going to be a matrix instead. So just to briefly highlight the way that we're doing our implementation, rather than using the Mitsuba, which again takes on the orders of hours to render, we're using Apple's Metal framework, which is designed to take advantage of the data sharing on Apple Silicon chips with shared memory management. So easy communication between CPU and GPU, and is supported with Apple Vision Pro, so we can kind of immediately port this to AR, VR, and test the applications of this research in real time with like a AR, VR headset. With the drawback that it is, while free, specific to Apple devices. So to really relate this to what we're doing in class, I wanted to talk about the different types of lighting models that we've learned about. So when we talk about like Phong shading or blend Phong shading, what that really is a scalar bidirectional reflectance distribution function, and that is describing how light reflects from the surface based on the incoming and the outgoing ray directions. And so like this, can anyone spot whether this is Phong or blend Phong? It's not blend Phong, it's Phong. So the blend Phong, this would be the half vector. We're using the normal vector, which makes it Phong shading. And there's our Phong exponent right there. So this is an example of how we get like those specular reflections if we're not talking about polarization. And this also kind of takes advantage of something we call the microfacet model, where we can model texture by describing the macroscopic surface as a bunch of microscopic surfaces. So this is what we were talking about with like texture mapping. This is the same idea. And then we talked about how we can use the half vector, the vector between the incoming and outgoing ray, to simplify this calculation. That's what the blend model does. And that half vector is also really useful in parameterizing how the light will interact with the scene. So to highlight that, we have our, this is our matrix valued polarized BRDF or PBRDF. And it's parameterized using the Rushinkevich angles, which given an incoming and outgoing ray, we can talk about that half angle. So that's the angle halfway between the outcoming and ingoing, the angle of incidence, the theta difference, and then also we can talk about out of plane scattering. So if the rotation around the half vector is less than 180 or greater than 180 degrees, that means we have out of plane scattering. And so we talked about all of these different examples, how light might bounce around and there are different probabilities of that, and that's what we do in like more complicated ray tracing scenes. And this is basically talking about the probability of that and how that happens. So in this simple BRDF that was created by one of the grad students from our lab, he developed this analytical polarized model. And much similar to kind of how our Phong looked, we actually have a really similar form in the polarization. We have this specular component, and this comes from the Fresnel surface reflection terms, which basically is just that, how much based on the polarization gets reflected versus transmitted. So this is treating the reflection as perfectly specular. Then we add a diffuse component. We also have this weighting term with some sort of sign to an exponent. Now, this would be a cosine for the Phong model because you have all of the specular reflection at that 0. Here, it's a sine because the diffuse reflection is increasing as angle increases. And so here are the values of these parameters, the refractive index, A and B, based on just kind of testing in the lab on like red 3D printed plastic. So now kind of putting this all together, I want to move on from the math. How this actually works, I want to get into like the demo, the cool part. So here is a example of the Cornell box. This is a really common thing that we use in rendering as like a test case, much like the Stanford Bunny. It's just a really good 3D scene to test ray tracing and lighting algorithms. So here's the RGB version. This was rendered using CUDA, and here's one of our early ray traces in metal before I added in all of our polarization math. So this is just kind of a purely radiometric intensity rendering. Then I had to take this scene and basically do all of that math that I was talking about earlier, the biggest piece of it being calculating all those angles. And so here is, I'm not sure why, there's like some weird aliasing going on in the projector.
This projector has its sense of humor. It will filter out some colors.
It does not like the blue.
It's a little bit on orange too, though. It's really strange.
So here's a map of those Grushin-Kievich angles.
It's like getting worse. That's all I can say. Sorry.
The depth map that we saw from Homeworks, and these are just kind of pretty rainbow images. I'm going to move on because that's tweaking. So here are 3 different intensity renderings now using that BRDF that I gave the Jarecki model. This is for a red object, so 632 illumination from this source, and I'm changing the polarization of the source. So in this image, the source lighting is all horizontally polarized, vertical, and completely randomly polarized or unpolarized. And you can see that when we're just doing ray tracing, so there's no global illumination in this right now, that's like our next steps, the polarization effects are pretty apparent for just those first surface.
Just to connect, since last class was, I think, the first time they mentioned global illumination. Global illumination would assume that the depth of the recursion of the ray tracing is unlimited. Everything shed light on everything else that shed light on everything else. And the colors is the merging diffusion of all the colors that each of these paths have passed. So that would be the global illumination.
So right now,
do you want to point out the global illumination effect on the Cornell box? Because I think that was pretty essential to how they develop it.
Yeah, so this is the Cornell box, and part of why it's so commonly used in rendering is because of the complex global illumination effects. We can see the effects of shadows. We can see how the green light from this wall is reflecting onto this and changing how we perceive this surface to be a little green, this surface to be a little red. That's all global illumination effects.
Like those are not painted boxes, right? Those
yes.
are assigned like the same color as the wall and stuff. That's all. Simple way to understand.
So these are those intensity renderings, and what it's doing right now is it's just firing all the rays from the camera and then connecting them to the light source. So these are not necessarily, and they're definitely actually not the most probable paths for the ray to take, but it is this like effect of the direct illumination from the light source, which is what's changing polarization here. The next thing I do is I can take an analyzer filter, which you can basically think of as like a pair of sunglasses. Sunglasses are like a analyzer filter in that they're filtering out a specific polarization. So imagine I have a really, really strong polarizing sunglasses where we're going to block out 100% of the light that's oriented perpendicular to our analyzer. So to visualize that, if I put a analyzer filter horizontally oriented, this is what we get. We don't see a ton of change in the horizontal illumination. It's still really bright. It's all still getting through. But the vertically polarized image, most of the light is getting blocked. In our random polarization, it's a little darker, but we don't necessarily see, like we can still see a pretty bright scene, like what would happen if you had sunglasses on. If I put it at 45, you can see that both of these get slightly attenuated, although they're kind of in different directions, which I think is interesting. Like it's dark this way, and then on the horizontal we see that it's light. And then in the randomly polarized, we kind of have, instead of a 4-petaled pattern, we have like a 2-petaled pattern, or 3-petaled pattern. So really interesting kind of effects, and then continuing to rotate, if we get to 90, now our vertically polarized image is the brightest. The horizontal, we're totally blocking out. See how this has gone completely black, because we're blocking out all of the horizontally polarized light from that. And still not much change with our randomly polarized image. And then I'll animate that effect so you can see what's happening. And these are all synced up. So when the vertical image is brightest, that's when the horizontal image is going to be darkest, and vice versa. And at 45, we're at equal attenuation in both.
So that's like me looking at it with polarized sunglass and rotating the sunglass.
Yeah, if you had really strong polarization, a really strong polarization filter in those sunglasses. Now, obviously, the effect isn't this apparent in a normal room because all of that ambient light is unpolarized generally. After the light scatters and scatters and scatters, all of that polarization eventually becomes scrambled, so we really only see small amounts of polarization. But really obvious sometimes, like if you've ever put sunglasses on and looked at your dashboard and like certain lights you can't see, that's because those lights have been polarized. Another way to visualize this is with Stokes images. So here, again, is talking about the Stokes vectors with the Q, U, and V components, horizontal, diagonal, and circular. If I have on the Poincare sphere, so I'm going to move around the equator and cycle through the different, going from horizontal to vertical illumination. Hopefully it loops right. Yeah, let's go. So we can see how it goes from horizontal, and then the blue is all vertical, and the circular is really dark because most common indoor objects, again, they're not creating a lot of exotic polarization like circular polarization states, and we really just don't see circular polarization in the environment very much. It's mostly linear. However, if I did want to see what circular polarization looks like, now I'm going to go from the bottom, the south pole, with left-handed circularly polarized light, up across to the north pole of the sphere, and change my light source to be right-hand circular polarized. So we can see it goes from really dark blue all the way up to yellow, or from light blue all the way up to yellow as we go from the south pole to the north pole. Another cool effect that you can see here is on the edge of this. So like I said, I haven't gotten to global illumination, which would kind of drown out this effect, but it's really obvious right here that when the light hits the very corner of this sphere, or this cube, it becomes highly polarized, and it happens to become very highly 45-degree polarized. But that's an example of how at really high grazing angles, that's where we see a lot of polarization, when you're like just kind of at grazing incidence. If you have like a direct on reflection, a lot more is going to get scrambled, and not. So that's one important thing to understand, is that materials are not always going to be depolarizing. They can also induce polarization. Going forward, here's our actual physical Cornell box. So we can actually do measurements to like figure out, hopefully, the like measured values, empirical values for the polarized BRDF. So this is a tool we have in our lab. This is a very fancy polarimeter, meaning it measures polarization. and we can look at different camera angles. This thing rotates out, and here's our source, and we can change the wavelength of our source, which allows us to kind of test to make sure that these renderings are accurate to real life, since we can't actually see the polarization with our eyes. We only know it's there from polarization filters and things like that. So we're still working on kind of updates to our acceleration structure that will allow us to move towards full global illumination with bidirectional path tracing. And right now, all of those renderings that I showed are still using those 4x4 Mueller matrices. And so the idea is to take these measured values for the Mueller matrix here and actually perform that Jones decomposition and demonstrate an improvement in runtime by August when I present at SPIE. So yeah, that's all. I just want to acknowledge my PI, Meredith. Thank you for coming over to CS. I walk here every day from the optics building. And Matt Kopinski, who's written a lot of the backbone for the code that I'm working on. This is supported by an NSF grant for the polarization lab over in optics. So I want to acknowledge the NSF for that. And acknowledge, of course, that our land is stolen, and that that should kind of, I think, is really important to thinking about the world and how we live and interact with our environment. Yeah, are there any questions about this or that I can explain?
Yeah. What sort of performance are you getting out of the direct path traced models?
Yeah, so right now, we do have real-time capability. Like I can, if I just pull up the app, you can see as I drag. So this is, when it's in drag mode, that's at rendering an averaging 20 frames. And then when I let go, that's a real-time convergence for averaging 200 frames. All of what was in the video was 1,000. And so here's a real-time performance of averaging 1,000 frames. So here's 20, and then when I let go, that's, so if I do a render pass, this has our statistics. So I'm doing 800 million rays per second right now, and I can generate 400 almost frames per second.
Are you doing any type of like interpolation between the trying to figure out the polarized values for places where you don't get like a ray yet? Or?
Yeah, so that's a really good question. Part of what is so important is because of how some of the values are connected in the Mueller and Jones matrices, you can't just interpolate values because you'll get physically implausible geometries and things like that. So one of the advantages will actually be able to do more physically accurate interpolation for non-rendered geometries by using the Jones approach.
Those Mueller matrices he was showing, if you just randomly generate numbers and populate a real value 4x4, the probability that it's a physically constrained Mueller matrix is like single digits. Does that make sense?
Yeah,
so you can't just take two Mueller matrices and do a convex combination and stay in the physical space.
That's pretty cool.
So it makes interpolation a challenge.
Yes, lots of convex sums and weighting using the different weights. So like that's the TD model, is it's essentially a convex sum of all of these different eigenvalues, and by reducing it from 4 to just an ideal depolarizer and then this one polarizing element, the dominant polarizing process, we capture the bulk of the polarization information so that we're maintaining physical accuracy, but we don't have to render all these, over-parameterized Mueller matrices, which has more information than is going to be found in common environments.
So, two questions, and I'm not sure that any of them lead anywhere. Do you think about it with white source separation?
What do you mean?
Example of white source is I am looking at what's happening outside through the window, but in the window I'm also seeing the reflection of something. Or another classical example of white source is I have a few microphones in the room and I'm trying to listen to one particular conversation despite the noise of another one. So the example was looking at a scene where what I see in the camera is a combination of a few sources, like reflections of something plus what you see through the window.
Yeah.
Like what you see through the water. So that, yeah.
So that's part of what we're trying to see is, if, I like the lamp as an example.
Yeah, the reverse from the generating, it's a synthetic generate.
Yeah, because you want to be able to know how polarized light that's now reflected off of this laptop is going to interact, because this induced polarization is then going to affect how that ray would interact with the next surface. So yes, you definitely want to do what you're talking about. Was there another one?
Can you go slide 14?
14.
How many bounces are we doing? You were doing recursive ray tracing off like you were pointing out how you could see the green on the and the red.
I didn't render this. I found this online. And the note, this is from Wikipedia, and the note was this is an incorrect BRDF, and I was like, well, it looks good and it's a good example. But the original Cornell box came from a paper in 1984, and then in 1985 they added these two cubes. But it originally was just a empty room with a blue and red wall, and they changed it to green because the human eye notices more subtle effects in green than blue. So they changed it to green so that you would be able to notice more of that stuff.
I think that what Ben wanted to ask is, remember from last meeting that the global illumination will completely abandon the ray tracing. It said there is a flow of energy from this surface to this surface, and if I solve many linear equations, many coefficients, then the result of this system is exactly so. It completely abandoned how many reflections.
No, so we would be doing full bidirectional path traces,
Okay.
using Reynolds light transport theorems, because we're not trying to do a bunch of linear systems modeling for the light, because then we kind of are losing that physical accuracy in the physics ray tracing and Monte Carlo methods that we're using. So it's a Monte Carlo approach rather than a global illumination.
How or where are you sourcing your BRDF data for the polarized models?
It was done for a dissertation of someone who graduated from our group, Quinn Jarecki, last year. Am I saying his last name right? Mm-hmm. Okay. Quinn did this for his PhD and has a ton of awesome theoretical stuff that we're okay, now can we take this and use it for computer graphics applications, basically. So he has a lot of measured polarized bidirectional reflection distribution functions.
Do you remember what wavelengths the study was?
Meredith, you would know.
Yeah, it's 3 visible wave bands,
okay.
And then an IR wave band.
Awesome.
And I think the band pass for the measurements, it's an LED illumination, so I think it's 25 nanometer band pass, something like that. Kind of broadband, visible.
Awesome.
Red, green, blue.
Yeah.
IR.
Yeah. So if we know how the object behaves at red, green, and blue, then we can do RGB illumination.
Which the polarization is very wavelength dependent, just based on thinking about, like the relative first surface and diffuse reflections, and the first surface ones being more polarized. So like black things are more polarized than white things, right? So you get kind of an inverse with the degree of polarization and the radiometry in general.
Yeah, all of these, I mean, if I go to that table on the previous slide, everything here is totally wavelength dependent. You can see the weighting for the diffuse, especially, if this is a red object, there's going to be more red diffusion than blue.
Yeah, I think that is for a red object.
Yeah, well, yeah, 6.
Well, that's the wave.
Oh, yeah, no, this was the red.
Yeah.
This was, yeah. All right, well, if that's all, thank you guys for listening to what I do and tolerating my very specific questions that all have to do with this application. All right.
That was great. Thanks for hearing. And hopefully everybody took notes. I let you write 50% or so of the exams.
All right, well, you guys still have the lecture, right? Okay,
thought-
thank you
did
for
you-
having me.
Yeah,
Well
thanks
done.
for stopping.
Thank
Yeah,
you.
and that's true, yeah.
Oh, she was in your seat.
She beat me to it.
A different question. So far, I was recording it. If you don't want it available.
You don't post on YouTube that much, right?
Eventually, I'm moving it to YouTube. I mean, to find something in this YouTube is. So,
You did a TED Talk?
You did a TED Talk?
11 years ago.
it's
You did a
Tucson.
TED Talk? You did a TED Talk?
It's it's maybe I spent a few minutes because it's stuff that are still relevant and it has enough graphics involved, so maybe spend a moment. We had a cool system that is still alive, and and did you look at wireless communication? If they would care about it, I will talk to them. People are talking conversation with wireless people and moving to from 5G to 30G to very low. They are very much concerned with polarization as a way to increase.
Oh,
so
yeah,
it has it could go to different directions, even when you're talking about indoor, very high bandwidth, 30 gigabyte, 30
Yeah.
gig, very short waves.
When you have an optical system, like the light will be polarized, but like our research is specifically for like common indoor scenes where, like in optics, over and offside, like everything we do, everyone knows.
If you can write a simulator that will give me better way how much repeaters that they like relay, but are pretty passive for doing little things. How much can I merge them together and get better signal at night and simulate these parts quickly for 3D scenes? I know people that might like it.
Have you had the same glasses for 11 years?
It's not the same lenses, but
Okay.
the frame, yes.
They got thicker.
Yeah.
That's so impressive. I've broken my frames like 3 times.
Okay, so we had this hello nightmare. We talked about it. That there is result of the smoothing function that happen just near the object, and we thought the pixel right here in between. It knows that the pixel is in the sky, not in the tree, but when it wants to do a smoothing filter, low pass filter, it takes the average, weighted average, convoluted with Gaussian, etc., etc. This pixel looks at itself, but also takes into account some of the pixels of the tree, which affects the low pass, which in turn affects the high pass, which at the end of the day give it much higher intensity near the tree. Just because I started by computing the average, everybody in 20 pixels neighborhood of me should be in the summation. And last time we talked about how we decide that if a pixel are too far away from my value, but too far away now would not be that if a pixel pi, and I look at, here are the intensity, here is my intensity of pi, and pi plus 1 is more or less the same intensity, while pi plus 2 are way stronger. Then I can hand tune what is this too strong for me, and maybe in the average of pi in the smoothing, I will only take pi plus 1, but avoid taking pi plus 2 because this gap is too large for me. So I will not add it, and as we said, our cost function would be the sigma of the intensity of the pi, where pi are, we call them useful, so for average or S of pi. S of pi equals the sum of all the pj, which are pj in the neighborhood of pi, so that's pj, sum up to the intensity, and you want the average, so you divide it by what? Usually we are just, each one times the weight of pj, how much we want to give it, given that the distance between pi and pj is blah. But if we decide that pj is useless, then the weight that it should get is 0. Well, the original weight of all that I computed, all the wi's, should sum up to 1. So what should I do? I take S of pi, look at the summation, and divide it, normalize it by the sum of the wpj, weight of pj, where pj was useful. Pj is, of course, in the neighborhood of pi and useful. Everybody remember it? That's very convoluted and confused whenever I try it here, and it will be even more convoluted just because of too many indices. It was much simpler last meeting when we just had a single parameter function, parameter only of x. So what are we doing here with a Gauss filtering? So I can decide, hand tune, to say that if the intensity of something next to me, next to pi, if the intensity is so much stronger than my intensity, then I don't use it at all. And if the intensity is below the threshold, then I use it as a normal pixel, sum it up. And of course, we don't like such step functions. We cannot do, they are not derivative. It's very sensitive to user-tuned parameters. Instead, what we like as a function that the larger the larger the x is, the less weight they are getting, we'll have Gaussians. But it's not the Gaussian of the convolution. It's not the Gaussian of the tent that I'm putting on the pixel of the image and compute the tent. In terms, I will look at what I want is, here is my original input. Lot of pixels, the height is the intensity. It's RGB if you wish. A lot of intensity here, so that's maybe, that's a tree, that's a sky next to it. There is a clear cut in between the tree and the sky. If right now I'm doing the convolution with a Gaussian, normal convolution as a smoothing, that is, I got a weight of third, my neighbor got a weight of third, all of us get a weight of third, and summing up. That will not be a Gaussian, it will be a box, but that's a Gaussian. That's the convolution function. Gaussian just says if a neighbor is a bit further away from me, further away geometrically, I'm not looking at the intensity yet. A neighbor is further away from me, the less weight it is getting. But theoretically, even very far neighbors still get tiny bit of weight. However, looking at the tree and the background as a step function with clear boundary, convolve it with a Gaussian, and you're getting a function that gradually changes, creating this blurriness. Okay, so what are we do so once again, what can we do? What a new value is that we are sigma for all the pixels next to x, that is at x and sigma, that's the weight, that's just a Gaussian, just to give it function. C here is how far away I am from a point x, it is the x, and I want to ask if the C happens to be at a place, at the sky, where x is on the tree or vice versa, and the gap is too large, maybe I don't want it here in the sun. So instead of having just this, the Gaussian, what should we do? Skipping up a few times. I'll have the function, the same function that we had before. 1 over k of x is just how much weight could I accumulate from the useful pixels. How much weight can I get from the useful pixels? And my decision about the pixel being useful or unuseful, in this case it was a Boolean decision. If it's less than this gap, it's useful pixel. More than this gap, unuseful gets 0 weight. Instead, I will compute that the convoluted value of x would be the sum of all the neighbors next to x, the intensity of this point, I of x, and here is a new term, Gaussian of intensity at c minus the intensity of x. So that's a new term. That's why it's biliteral function. So G will say, if at c you're outside on the sky, and in x you're in the tree, and the intensity are very different, then even if you add it in the smoothing, don't give this I of x much weight. This parameter, this Gaussian, and this Gaussian doesn't care about where what are the x and c, where in the image I sampled. It asks what is a gap in the intensities between the two of them. And if the gap of the intensity is large, then G will be very small. Make sense? If the intensities are small, then you don't penalize it. You treat it as a normal pixel. It gets almost the same weight of, at least you don't extra penalize it more than the normal convolution, say 1/9 to each one of my 9 neighbors, 1/9. But if one of these 9 pixels is very different than me in its intensity, I'll give it less than 1/9 weight. So what does it look like? It looks like here is again the tree and the sky. Start from the original, and they just do the normal Gaussian, that's a f of xk, the Gaussian averaged. But now I'm adding to it another Gaussian that, we say, difference of intensity is large. That was the original weight for this pixel, but since the gaps between the center pixel x and c, since the gap of the intensity is large, then instead of having this Gaussian, push it down to be almost 0. Cool? So the convolution would look in this example as half a Gaussian, meaning that you respect the boundaries between the tree and the sky. You don't blur the boundary between the tree and the sky because your convol function adjusts itself to the value between the tree and the sky. But what happened to the Gaussian? But let's compare these two Gaussians. What's the difference between them? This Gaussian is, of course, central symmetric. It still doesn't look at the intensities. And presumably the sum of the weights of everything here is 1, so it tells you some desired heights of the individual pixels. What happened here? If I pushed down half the Gaussian to the floor, then the other pixels should go up, should be more important. How do I make them more important? That's exactly the value of k of x over here. What is k of x? K of x is the sum of what was the original Gaussian that I mean, times the penalty that I give to this Gaussian. If it doesn't get, if you have pixels that are very different, sky versus tree, then this will be very close to 0, meaning that this value k of x would be smaller than 1, meaning that now when you are computing j of x, dividing it by a number smaller than 1 will give much more weight to the pixels that you are using, to the pixels in the tree. Okay, I'm not sure that it's possible to understand what I said unless you saw the 1D explanation. Okay, and that's the idea of the bilateral filtering. That is, that you have two Gaussians involved. One Gaussian or tent or box or pyramid here that works about a location of a pixel versus a location of pixels nearby. And this Gaussian that doesn't care about the location of the pixels, but cares about the gap of the intensities between the pixels, says pixels that are very far away don't combine them or barely combine them in the overall weight. And don't forget 1 over k here, whose only purpose is to make sure that we are still doing averaging. It's still a convex combination. So the sum of this times this times this sum up to all the pixels still sum up to 1. Why do I want it to sum up to 1? Because if I start with an image that is uniformly blue with some intensity, I want to end up with an image that is uniformly blue, exactly the same intensity. Okay, another example, I mentioned it last meeting, another example that I use a bilateral Gaussian would be that actually this boundary is not the boundary between the tree and the sky, or one region of the image and another one, but this boundary is actually the boundary of the image. I just don't have any pixels over here. So I still want to compute the smoothing, the averaging at x, but only pixels at this region can participate in the game, can be summed up. Images that are pixels outside the boundary of the image should just not be accumulated. There is no value associated to them. Cool with everybody? Okay, yeah, so we are done with bilateral function. I have a little question for you, very unrelated, that after the course, and let's start with animation. Sorry?
Is it about mantis?
No, but not far away. It's about huntsmen. Do you want huntsmen?
Yeah.
Okay.
Yeah. A huntsman.
A huntsman.
It's a big spider.
Huge, very, very fast, harmless.
Are they native here?
Yeah.
Oh,
Yeah.
Have you ever tried to catch them and they run away really fast?
no.
With the long legs.
No, those are dead ones.
They do have long legs. They have like the flat abdomen part, so you can always tell which ones they are.
Look 'em up.
Yeah, also known as crab spiders. They have a very funny walk.
Oh, like you. Or furry.
You don't like spiders? I love them.
What's that one spider scorpion kind of cross between them?
Oh, the camel spider?
No, it's not camel spider. It's like a whip scorpion or something.
Oh. I think I know which one you're talking about. All I know is the camel spiders.
Camel spider's kind of close to it. But they're neat. I saw them a lot in Australia, but I haven't seen them.
You lived in Australia?
What?
You lived in Australia?
I did not live in Australia. I was just in
There.
Australia.
Why?
Because you can.
Free will. That was your exercise of your free will.
To go to Australia, yeah.
Okay.
A lot of fun spiders. Long legs and such.
Were you also in Australia?
Yeah, my dad's.
What?
Just
The only one who wasn't in Australia?
Yeah, we were hanging out.
Yeah.
You didn't get the invite?
Have you seen like the gigantic wallabies?
Yes, I know what you're talking about. Yeah, those are
Never seen it.
gnarly. Yeah.
That's so interesting. Were you born in Australia? That's cool.
We have a
I moved here.
translation problem. I have an object that moves at t equals 0. This object starts at p1, and at t equals 1 it will reach to p2. We saw this mantra many, many times. Here is a function that linearly moved from p1 to p2 in a constant speed if t change dramatically. So translation is easy. It can work on points on 3D, 4D. You can make it move along a straight segment, or you can move it along every one of the different curves that we saw. Linear interpolations, it is very safe. What happened about, so if I'm blending animation and all my objects do nothing but translation purely, I'm very safe of moving linear, using such equation or by just linear interpolation. What happens if my object also rotates? Now it's a big can of worms, because what can I decide? Here is my object facing from the center toward B. Here is my object center from the, placed still at the center, but looking at A. And I would like it to rotate linear rotate in a constant speed around this circle. When everything is still in 1D, I'm still not too, it's still not too complicated, but here is one thing that obviously will not do. So I want to, again, t equals 0, my object face at B, t equal 1, my object face at A. The object doesn't move, but is rotating. And I want to decide at every time I want to generate multiple frames, I want to decide for each frame which direction are you looking at. Naive approach, let's connect A and B by a segment. Connect A and B by a segment. Place a move in constant speed along the segment. And now you're generating every time t, like a t equal 0.2. Here is where you are along the segment between A and B. Look at this vector, that's the direction. Well, you can normalize it so it would be a unit vector. And now just move the point along the segment, and each time that dictates which direction you're looking at. So far, the only issue with this problem, I can figure out exactly based on this point at which direction are you looking at, but the rotation speed is not uniform, right? The rotation speed on the between A and B is uniform. The rotation, the angular speed is definitely not. You see that here between B and the first intersection point, I'm moving very little. Between the second and third intersection point, it's pretty large arc, much larger arc, and now they're getting shorter and shorter again. Okay, but that's somehow you can normalize. The real messiness starts when we ask about interpolation between two orientations. How can I define an orientation in 3D? I can say there is some person locked back inside the sphere. There is some direction that this person is looking at. That would be the direction in this unit sphere. And that's the source, that's the direction. And now I can interpolate using even what we just described before, that between 2 points like Q1 and Q2, if Q1 and Q2 are very close to each other, then all these linear interpolations are not too bad. You can interpolate by segment and slightly correct it. But lots of various disasters can happen if you want your character to move from one orientation to another orientation in 3D. And to start with, the extreme point is that it's completely not clear what would be the path, or that I'll move between them, right? That if it's a sphere and I'm moving from one pole to the other pole, there are many shortest paths that connect between them. Make sense? So one problem is that just specifying the source and the target doesn't give me any information about, or give me a lot of options about what is a track that what's the trajectory that I'll follow in 3D, because I'm living in the sphere. Looking at t equals 0 looking up, t equals 1 looking down. In between, I can look at this way, or I can move it this way, and so on. Triangle inequality doesn't hold that conveniently. The shortest path is not a straight segment in between. It's the part of a big arc in between, but all of it is still things that you can get, that is. And again, you feel it when you try to interpolate between angles that are far away from each other and are in 3D. So just to mention, jump over it, you can fix it in small orientation, yeah, sorry, I remove this slide. Between small angles, you can kind of get away. You can get other question is, let's use Euler description. What is Euler description? I'll tell you rotate first around the x by some amount, then rotate by y by some amount, then rotate around the z-axis by some amount. That will give me one orientation. And similarly, I'll tell you the destination as Euler coordinates, rotate by x, then by y, then by z, three other parameters. And I can interpolate separately by what I moved by x, what I moved by y, what I moved by z. And anybody but you can see what can go wrong here.
Depends on the order.
Gimbal look. You can get a position where you cannot continue rotating. You have, if you think about the three rings of the gimbal lock, you'll have two rings that are coplanar, and then you cannot continue rotation. So we can, so basically using only Euler coordinates, again, doable if your source and destination are close to each other, not in angle space, not close to each other, bad things can happen. And even if they are close to each other, you want to look at the XYZ. And most softwares like Blender will ask you at which order do you want the Euler coordinates to be, first by x, then by z, then by y, or which order, and then if you can decide at which order there is less likelihood of gimbal locks. That could happen even in small angles. What is a textbook answer? Use quadrillion that I am still yet to find a good way to get it, because I can show you the math. They are similar to convex numbers, some extension of them. I can tell you that you can move from Euler angle to quadrillion representation and back, and then when it's in quadrillion, then linear interpolation works without any gimbal lock, and then you are safe. And use the libraries to do it if you want to do animation without worrying about gimbal lock. Just move to quadrillion representation and use this part and use it as a strong library. Like, it's very easy to define quadrillion. It's much, much, much harder to ask why linear interpolation works there and in constant speed along an arc, and why gimbal lock will be much why gimbal lock will not happen. So after watch a bunch of other people teaching it, once again, easy to give the taste of look how cool it is, much harder to convince you why it is cool and why it is useful. So just as a motivation, it's important. It was last supported by people in Apple that wanted to check from the accelerometers if your laptop drops, what happened to your laptop and how many rounds it happens until it hits the floor. That was apparently another reason to put money and to have it in a robust way, because it's legal argument your warranty is void or not void depending on what did you do to your laptop, etc. Good things, very important. Not something that I could have in a couple of hours explain why this is better than Euler coordinate. Okay, so our next topic would be animating forward and backward animation. If we have a skeleton, how from the skeleton I can decide about the angles and ask what the skeleton will look like. At the next part, that was easy, or the backward animation, I'll just make this movie play for 30 seconds and send you home.
Okay, so let's get to it. Both IK and FK terms
Is,
come from robotics, where engineers have to figure out how to move and rotate joints to get the end effector to the position they need. When you think about it, if you try to grab a phone on your desk, you don't have to compute what your joints have to do to get your hand to the phone. You just do it, because it's natural for us, and we learn that gradually from birth. However, for a robotic arm,
interrupting it for a moment. If I'll ask, where is my hand, given that these and these are the angles of each part? If I'll ask where is my arm, that's a very easy calculation. And if you tell me second later, these will be all the angles, asking where is my arm is also a very easy calculation. But that's a forward kinematic. From the parameters of each joint, determine what is the robot's arm is. The reverse animation, the reverse kinematic is way harder. It's to ask what should be the angle of each part if I want this movement of the hand to be, what should be the angle of this joint, and that would be the reverse kinematic.
not that simple. There is a lot of math behind it, which we as an animators don't have to understand it. Bone chain is rigged with FK. It means that the bone chain rigged with FK is useful is that it creates arc movements by default, because you use just rotation in between IK and FK for its limbs. CAD provides this option automatically for each limb, but every animation system has a way of doing it, whether it's Maya, Motion Builder, Biped, regular KBS Max Bone, or anything else. So in CAD, if you select any bone of a limb, in Motion Panel you will find this IK-FK slider. We see that now its value is 1, which means it is fully in FK. If we select the square, which is our IK and effector, and try to move it, nothing happens. Well, that's because we are in FK. We can animate each bone in that parent-child manner, as we showed in the beginning of the video.
So, yes, of course, the forward kinematic, specify what the angle.
Now, if we try to move the slider to 0, so the limb is fully in IK, and then move our IK effector, we see that the arm is moving and that it is trying to reach the effector as best as it can.
That's the position that I want to be, and the backward
if you don't have this end effector for a limb at all, don't worry. When you are creating a new rig in CAD, legs get IK platforms by default, but arms don't. However, if we go to the motion panel with any of the arm bones selected, you can see this Create IK Target button. Just click it and cross will appear. You can choose between cross or platform in Modify panel, whichever you prefer. Okay, so in CAD, by default, arms are in FK and legs in IK. If you move pelvis, you can see that the legs stay on the ground and everything else is moving with pelvis, because pelvis is a parent for all the bones. You will realize that it is usually more useful to keep legs in IK, because in a real world we have gravity, and that keeps us on the ground. Unless you are doing some roundhouse kicks, underwater animations, or something like that, you can keep legs in IK. That's it.
Okay, maybe we'll continue, otherwise you have the link to this video. Everybody understood what? The easy part from angles where it is located, hard part, if that's a motion that I want of the hand, what should be the angles of each of the parts to create the smoothest motion, and in this case we are not going to get to it. Classical problem with robotics, solved for many years, the backward kinematic, you know what it means now. Okay, we'll talk about animation of particles and physical-based animation later, and how can we simulate cloth that is moving and water and non-rigid body. We'll see some uniform approach to all of them. Thank you. Thanks for being patient with the time, and thanks again for
When you see this video,
I'm used to wolf spiders. Whenever I go to Montana, they have like millions of them on
you're
the
blue and brown.
What?
Keep going, please.
Australia was once. I'm constantly in like Montana.
Fantastic.
Yeah, there's
Is that where you're from?
There's a
Fishing.
Technically
Fishing?
Yes.
Why?
What do you mean why?
Like, you can fish anywhere, can't you?
Yeah, but like Montana's like, great.
You're not from there, you just go there and
Yeah.
fish?
So I'm originally from like just north of LA.
No,
but
you can't.
What makes you choose Montana?
What?
What makes you choose Montana?
Why did
You know,
what?
Like, what made you choose Montana for fishing?
do
Well,
something
it's like
that
Montana,
is
Wyoming,
useful
Idaho,
for
like all
everybody.
like the Rockies.
Yeah.
Okay, because I was like, you could really fish anywhere.
It's
Not really Tucson.
the responsible thing
I
they
see
thought
people
for my
fishing in
part
like
was
Silver Bell Lake all the time. You
It's
don't want
depressing.
poopy
that
fish?
if you need
Oh,
a
it's
this type of
depressing.
animation,
Poopy fish?
Well, it's
go
like the
back
one
and
with
forth
Lake on Mount
from
Mountain, they have to like
Conquerando,
put fish in.
Yeah.
Yeah.
I tried fishing like
one
the
matrix,
bison
there is another
Tucson,
one
and like
between the
I
matrices,
drove an hour and a half to
you
down to
can
Patagonia Lake
interpolate
too.
Yeah.
I'm not fishing
linearly
anymore.
no
I'm
matter
moving to
what
Idaho
sort
for
of
like an internship for like 6
every
months. And I'm
intermediate matrix
I've been I live like somewhat in
Did you
Idaho.
look,
Yeah.
did you like
Location,
look
they
for
were-
internships in that area so you could fish?
Beyond it.
No,
It's
but
just
however,
like-
it
see
didn't.
many courses.
Yeah.
If I'm working to like
Yeah.
about less than 1,000 feet away from like a really nice river,
That's so
I'm
funny.
kind of inclined to go.
That's so funny.
Yeah.
You know, like learning
No,
more
the,
on
I like the
Australia,
video
for
because
some
it
reason,
like
that was
actually
like,
like
yeah,
you
that
can
makes
see
sense.
why it's related to a
Yeah, it was
rotation
like, yeah,
that you
that like
I'll
that's
leave it
just like I
alone.
was like, there's something
Yeah.
about it. Being born
I've
like
seen it
Australia,
once, but yes.
learning you fish
because it's a little
did
bit more
not give that
geometric
same experience
than-
whatsoever.
rather than
It is
like
like the complete
mathematical
opposite where I'm like,
or
this
like
dude
algebraic
fishes?
numeric.
Not like
I
a
can
bad
see
way,
that
but it's just
even
you don't
here
look like a
avoid
fisher
the
type.
wino game.
I'll take that as a compliment.
Yeah.
If I remember well.
You definitely
but
don't
it
look
was
right,
last
like he
year.
doesn't look like he fishes.
Whenever,
I'm not sure.
Yeah.
whenever I'm like walking railroad
So
tracks.
bored by fishing.
What?
Did
Yes.
fishing like twice, and I was
So
really
that's
bored, but.
sailing
you
of my
were
home
raised
right
in
now.
Yeah.
Uh,
I mean,
entirely,
also when I
yes.
was
There's
like
just a million
16, so
babies.
maybe all
Yeah.
kids and it's appreciated.
I would love one.
Walking around like railroad
That's
tracks in the middle of the night in like
Yeah,
Montana,
that's
very
Oh,
fun.
hell yeah.
Okay, so how
That's
big
like
is
10
it?
millimeter.
Terre
Okay.
That's one, that's.
Yeah.
It's
It's about
Yeah.
Because I
That's
can bring a
really-
little couch.
It's really nice because like the camera can't capture the color.
I'll bring a few. At the moment I
Anything
didn't
that will-
succeed to
So
feed
really
them
nice
anything,
at
but
They're
yeah,
so
I mean,
cute. Thank you so much. I'm so
and
excited.
I had
Kinda
a much
scary.
larger
Yeah,
one.
yeah, for us.
Just,
Okay.
Oh, yeah, just the bears.
Pretty,
yeah, it's
Yeah, thank you. I
very
love
cool.
them. That's so cute.
I agree.
I'll set
Yeah.
something up for him. Okay, thank you so much for the lecture. Bye.
Yeah.
Ain't
The
no
walking-
way.
walking-
This is awesome.
Walking around in the middle of the night in Montana, you see so